Okay, we're going to discuss today the convergence of the Muller algorithms. We want to look at methods that produce a convergent subsequence, at least in a range, and we want to predict the computational order of convergence. Methods we'll look at today, well, we're not going to discuss the first few. Fixed point method, bisection, Newton-Raphson, secant. We looked at that in a previous video. Today, we're talking about Muller's missing method and Muller's original method. We will not study the conditions that guarantee convergence, and we're not going to review the algorithms for this video. We're just going to take the formulas from the previous videos. This video will assume the knowledge of calculus and Taylor's theorem. And this video is based on original work as far as I know. So we'll define yn to be g of x sub n. And we'll define the law of motion for x sub n is x sub n plus 1 is equal to x sub n minus this adjustment yn over a1. a1 is a function of n minus 1, n minus 2, but we'll just drop the notation because it's too cumbersome. We'll just say a1. And this is the formula for a1. So x sub n is equal to the root plus an error term, which we'll call xi of n. We'll use that notation throughout. So a1 can be expressed as in terms of these xi n minus xi k terms, where k could be n minus 1 or n minus 2. Xi n plus 1 is equal to xi n minus the adjustment. Then we'll use the Taylor series expansion for g of x. And we'll use the fact that g of r is equal to 0 by definition of the fact that r is the root that we're trying to find. We'll expand the terms of a1 out using the Taylor series expansion for y of k. So when you do the math, if you see any term of the form bn times xi n minus xi of k, where k could be n minus 1 or n minus 2, it will cancel out, it'll divide out, and you'll just get the constant b of n coming out of it. Likewise, any term of the form bn times xi n minus xi of k raised to the second power, it will cancel to become 0. So let's look at the terms of the expansion a1 term by term. First, let's look at the first order terms. First order terms, very simple. It just everything divides out nicely. We get g prime, which makes sense because a1's supposed to be like g prime. Now let's look at the second order terms. We can factor it out, and then we'll do a little algebra. We'll put it into this form. The second term is 2 xi n minus xi n minus xi k. That means we can use our rule. The first term is a constant, second term is 0. So the first term, we just use our rule, and we get that everything turns out to be G prime psi n, which turns out to be exactly what you would get with Newton's method, by the way. Next, let's look at the third order terms in the Taylor series expansion. This is where it gets really interesting. Lot more work here. We can factor out a psi n minus psi k term, and we can do some algebra on that term just like we did before to get at least some simplification. The first two terms we can solve for that. But then we're left with that last term, psi of k squared. And we can't really do anything with that, at least not initially. We'll just have to multiply through, put it into the formula, and hope all the terms in the numerator cancel all the terms in the denominator. Now, two of the terms will factor out in the numerator, and we're left with this expression, and we'll combine them into terms that contain psi of n and terms that do not have psi of n. And then we'll simplify. We'll see if we can factor out a psi n minus 1 minus psi n minus 2 term in each term. We were able to do that in the first term easily, and it turns out it's true in the second term as well. So everything in the numerator divides, everything in the denominator divides through in the numerator, so we just get a simple expression. We get this nice expression for the third order terms. Combining the first, second, and third order terms, we get this expression. Now we can use this to plug in our formula for xn plus 1. First, let's transform xn plus 1 into a psi n plus 1 by subtracting r, and then get a common denominator and expand the numerator. And the constant terms, the first order terms, they cancel, and that's true in anybody's method. Newton's method, secant method, Muller method, but nothing else cancels. We see some simplification, but not cancellation. There's just a lot of terms here. Now, looking at this, we should ask which terms look small, which terms are smaller than the others. And I can spot that the psi n cubed term, that's small. Psi n squared times some other psi n term, that's small. But the two terms on the either side, they are not obviously small compared to the others. We'll just have to do some more analysis to figure out which one is small. So which terms are smaller? Well, we can use the fact that psi m gets smaller as m increases. That's just because it's a convergent sequence and it's converging quickly. So we know this is true, that but which of the following can we say? 1, 2, or 3, 2. When you look at 2, that is secant method convergence. We think it ought to be better than 2. it probably should be 1 because we're using 3 points instead of 2 points. It ought to be better than secant method, but that's just a guess. We don't know that. We have to prove it. So why don't we do this? Why don't we assume 1 is false and see if we get a contradiction? So we're going to assume 1 is false. If we assume 1 is false, then multiplying by xi n, we get this expression, and that implies 4. 4 has to be false also. But that means that if 4 is false, then maybe the xi n squared terms, they have to be the dominant terms. And we're in the world of quadratic convergence. So that means that xi n is order xi n minus 1 squared because of quadratic convergence. But we also know that xi n minus 1 has got to be smaller than xi n minus 2 because n minus 1 is bigger than n minus 2. And multiplying through by n minus psi of n minus 1, we get this expression. Now compare third expression with the top expression. We realize, oh, we get this last expression, which is 1. This is saying 1 is true. 1 is true where we assumed that 1 was false. There's a contradiction. So we can't assume 1 is false. We get that it's true even when we assume it's false. So it must be true. So let's assume 1 is true. Then we get that xi n plus 1 is proportional to the product of the 3 prior error terms. Take logs, and we get this interesting difference equation. It looks a little bit like the Fibonacci type equation, but it's 3 terms instead of 2. And that's called the Fibonacci sequence. And we'll figure out what the convergence rate of the Fibonacci sequence is. Well, assume that it reaches a ratio, and take a ratio of Zn plus 1 terms and divide through by d times beta to the n minus 3, and then let n approach infinity, and you get this equation, and the root of that equation is beta equals 1.839. So that's the rate of convergence of the Muller missing method. This last part is an interesting problem in itself. Let's see if we can figure out how to use the Fibonacci sequence to solve this equation. We'll just do a simple spreadsheet and see if we can get to 1.839 coming out of it. Okay, so here's the spreadsheet. And this is the formula for the secant method. We use the, we're calculating the golden ratio as the ratio of the result of the Fibonacci type sequence. But what we'll do is we'll just modify this code to be, instead of the sum of the previous 2 terms, the previous 3 terms. We'll bring that down, and see how that affects the calculation. And just like that, we turned 1.618 into 1.839. So that's the right answer. Now why don't we try it again? See if we do the first 4 terms and see what number we come up with. It's so simple to do. We get 1.92728. Okay, let's do the first 5 terms and see what happens. As you can guess, we're getting closer and closer to 2, but we'll never get to 2, of course. We're going roughly halfway to 2 each time. Alright, let's do the sum of the first 6 terms. And one more. Let's do the sum of the first 6 terms, first 7 terms. That'll be the last one we'll do. This sequence converges about 40 terms. So here's the table. This table was in that other video on the Muller Blunder method. So now we'll talk about Muller's original method. Recall with Muller's method, the formula for xn plus 1 is given by this expression. It's really complicated denominator. We will modify the denominator to make it look a little simpler. It'll look a little bit more like a1, and a1 minus another term, and then we'll figure out what that other term is. So we'll look at the denominator term, we'll do some algebra to it, make it look a little bit more like a1 times 1 plus another term that's small when y is small, and that term in the brackets we'll call b, and we'll do a Taylor series expansion on b because b is small. We have to calculate b of 0, we have to calculate the derivative of b and then evaluate it at 0. So evaluating at 0 is easy, it's just 0. The derivative, we just use the chain rule. And thankfully that expression on the far right that involves the negative exponent, that's just going to be 1 when we put y equals 0. So it actually simplifies quite a bit. B prime is minus a2 over a1 squared. Then we'll plug that in for the formula for d, and we'll discover that d is equal to a1 minus a2 yn divided by a1. Now let's look at a1 and a2, see if we can simplify it a little bit more. a1 goes to g prime, a2 goes to g double prime over 2. Yn is approximately g prime psi n. So when we plug everything in, we get the second order term. It looks familiar, it looks small, but let's plug it in for the xi n plus 1 term. And look at that, the numerator, well, the g prime xi n terms cancel, they always cancel in everybody's method. But the second order terms, they all cancel. This is different. All the second order terms cancel. It looks like an amazing coincidence, but that's what turns out to be, and the coincidence goes further. All the third order terms except the one you see there cancel. There's a deep reason for that. Won't go in for that, but it doesn't really matter. The point is that the order of convergence is the sum of the three previous error terms multiplied together, just like in the Muller missing method. We get the same result. We get the 1.839 convergence rate, same as before. Okay, time to close the spreadsheet. If you like this video, please give it a like, and thank you.